very tired.
I mean, it's almost 10. Come on.
I have work to do at night, so I don't sleep very well.
Gotcha, gotcha. All right, 9:45. Let's get rolling. Lord, thank you for bringing us together this morning. Thank you for letting us have a great weekend. Pray that you would carry us through this week. Help us get through most of the for most of us. Help us get through the online learning portion of the semester. Help us if we're continuing TOS to stay strong and focused. Lord, I pray that you would just give us the patience and the strength that we need to overcome the obstacles in our way. In your name we pray. Amen. All right. So today, today is it's a big day. It's a big day, right? We've turned in the homework for mechanical systems, and now we're moving on to everybody's favorite topic. I know, electrical systems, right? That's everybody's jam, right? Everybody loves cue groan sound effects, right? So when I go back and I edit this video for lecture, I'll put in right? Because I know nobody likes electric systems. But as much as you don't like electrical systems, you're gonna even love the next topic after this even more, right? Thermal and fluid systems, right? That's everybody's other favorite. So here we go. Jeff, people not getting Jeff. Oh, right. Before we start heading into this, let me say this. I'm working on the lab reports. I'm working on your homework, so I'll grade it as quickly as possible, right? So don't worry about that. Please don't bug me about it, right? They're gonna be done soon. You can always ask me, right? But if you want to take the grade that you have right now, right, you can, even if it's under. So I know it's a bad joke. Just don't ask about it. They'll be done by Wednesday, right? Well, at least the labs will be done soon, and the homeworks will be done shortly thereafter, right? So working as fast as I can, guys. All right, so there's that. All right, so Jeff, J effective, right? How do we determine an effective inertia, right? And I use that energy method in class, right? And that kind of threw people for a loop because we hadn't been talking about energy, right, at all. Well, if you want to create an effective inertia, that's how you do it, right? You need a third equation. You need an equation outside of the equations of motion, right? We can't equate everything to, right? So think about this. Go back to when you took statics and dynamics, right? If you didn't take statics and dynamics, what we're really doing is we're setting up systems of equations, right? And so if I have two unknowns, I need two systems of equations, right? But if I want to combine two of the unknowns that are in my system of equations, I need a third equation, right? I can't do that inside of the two equation system. I need something outside of that system as a third equation, right? And that is where the idea for Jeff comes from, right? Jeff is just taking these two things. I'm taking these two gears, right? And I'm smashing them together, right? In your mind, I want you to think of just combining both of these. So I'm going to replace them with a single inertia as if that first gear was rotating about the axis that the second one is rotating about, right? And so that's the whole idea, right? So instead of analyzing this piecewise, right, we merge it all together and you make it a single system. That's the idea there, right? I got caught up grading labs this weekend. I will, like I promised, post a video on how to do this problem that we talked about, right? Last week, the longer way, right? I'll go over that, how to do that, but I just haven't gotten there yet. It's on my list of things to do. I promise I'll get it done. Homework stuff. Well, I hope if you had homework stuff questions that you came to office hours, right? And you got those homework stuffs. You got those homework stuff questions answered. You guys may have noticed I posted an announcement yesterday in LoudCloud, right? There's week 1 and 2 example problems. I will give you the other example problems that are not included in those 2 documents later today when I scan them, right? Look for that announcement. Homework 2 is posted, right? That's going to be due in a couple of weeks. So homework 2 is posted. There was something else I put in there too. There's the 2. Oh, and the week 3 and 4 example problems, right? That we're going to, the electric system example problems that we're going to be working through, right? The electrical and the electromechanical system problems. This topic is in the syllabus, says it's going to take 2 weeks. We're probably going to spend 1.5 on it just to get a little bit of a jump start on thermal fluid systems next week, all right? And give us a little extra time there. You guys have any other questions? Damper, kinetic, confusing. You guys have any other questions? Anything that I didn't address here specifically? No. Everybody, all right. Everybody have a good weekend. Okay. I did, and I didn't. My fantasy football team won, which, you know, go Sons of Bloin, right? But unfortunately, the Giants lost to the Bears. I mean, what's going on, man? I mean, it's not unexpected, but I mean, they looked decent the first guy anyway. Okay. It is confusing. All right, anyway, so what do we got? Homework 1, right? We turned it in yesterday, or not yesterday. I keep thinking it's Monday for some reason. Turned it in Sunday. What do you guys got coming up? Well, we've got our ethics and system dynamics paper, which is an ethics paper. It's posted in LoudCloud, right? Please read through it. Please read the rubric. Essentially, you need to read an article and write a paper from the Christian worldview perspective as to whether or not it is appropriate to make assumptions when you are making models. You can take so I want to be very clear on this. Take whichever point of view you want, right? Take whatever point of view you want, as long as you can back it up with evidence from other sources, then I am fine with that. I am not a theologian. I am not a scholar of philosophy. I am not going to dig super deep into this, but you do need to make sure that you do the things that are asked in the rubric. I am pretty sure I have a slide here talking about it. If not, I'll pull up LoudCloud in a second. We'll go over it. All right. Homework 2 is due 10/4, right? That's not this weekend, but the weekend after. We've got exam 1, 2 weeks from Thursday. Exam 1 is going to be 2 weeks from Thursday. And homework 3 is due on the 11th, right? So that's going to be the Sunday after the exam. Okay. I'll post homework 3 in the next couple of days, just so it's up there. I don't expect anybody to be able to really do it since it's going to be on a topic that we're not going to start till next week. Okay. All right. You guys have any questions? Right. So this brings us up out of, this is it for the rest of how to model systems stuff, right? This brings us through week 5. These are the things due through week 5, right? They're going to be up here every class period from now until then, right at the beginning. All right. There we go. That's the one. Don't mind that ad. It's fine. Oh, it's gonna be one of those ones I can't skip, guys. I apologize. Listen, wait.
Welcome to the new YouTube.
Electricity. All right. So that was relevant because we're talking about electricity today. I know. I did not go over what is expected in the ethics paper, did I? Did I? All right. So let's do that real quick. I'll just go ahead and grab that. I'll give it a sec. Ethics paper. Okay, so what are we doing with this ethics paper, right? Because that seems confusing. Why is there an ethics paper tied to this class? Sure. All right, so you're going to review based proximity, beyond proximity, consequentialist ethics, and system dynamics, and write an 800 to 1,000 word essay on the importance of ethics in the field of system dynamics from the perspective of the Christian worldview. Bullet point 1, what ethical considerations should be examined when making a decision about a model? From the perspective of the Christian worldview, provide an example of a situation in which a defective product was sold and the ethical responsibilities of the decision maker. 2, should a procedure be in place for making model boundaries? Discuss a possible procedure for making an ethical decision. 3, is it ethically wrong from the Christian worldview perspective to make assumptions about a model? You must prepare this assignment according to the guidelines found in the APA Style Guide located in the Student Success Center. An abstract is required. The assignment uses a rubric. Please review the rubric. Okay. So look, you can read this yourself in Loud Cloud, right? But as I said at the beginning of class, I am not an expert in I'm not an expert in this topic, right? I'm interested to see what you guys have to say. I have my own opinion. I'm not going to cloud yours with mine. So please feel free to take either side of this debate, right? Whichever one speaks to you, as long as you can back it up with sources, right? You should be fine. Okay, that's what we're looking for. Standard ethics paper.
Are you going to be enforcing the word count pretty heavily, or is it just a kind of guideline?
So my view on word counts is that things should be as long as they need to be. But if you turn in 10 pages, then yeah, I'm gonna slap you, right?
Okay.
1,200 words. Word will tell me how much it is. I'm not gonna like fly off the handle. But you know, again, if you turn in a novel on this topic, which frankly I don't really see as being possible, but if you did, right, then we're gonna have words, all right? But otherwise,
okay. Cool. Thank you.
Sure. Okay, so what are we doing, right? Electrical and electromechanical systems, and our objectives are to create mathematical models of circuits using Kirchhoff's voltage and current laws, right? The voltage and current divider rules and loop analysis. And we want to evaluate the ethical implications of decision making, right? Because that's the thing that the ethics paper is about. Okay. So Electronic circuits and electromechanical devices such as solenoids and actuators are used extensively by mechanical and biomedical engineers for instrumentation and sensors, right? Well, I mean, you wouldn't use an actuator as a sensor, but you get the point, right? So we use electromechanical devices in a lot of different things, and we use electronics in a lot of different things, right? So what are some examples of this? Anybody? Anybody? Oh, I know the problem. You guys don't forget to unmute. Don't forget to unmute. That's what are some examples? This is a question to the audience. An example of an electronic or electromechanical device that is used in engineering.
Pressure sensor.
A haptic engine.
Sure. Motor, engine. Good. All right. So yes, right. These things are right. Just like mechanical systems, we can talk about these as being composed of elements, right? There are two flavors of elements in electrical systems. We've got passive elements and active elements, right? A passive element is an element that cannot introduce energy into the system, right? It can only store or dissipate energy, right? These are things like resistors, capacitors, and inductors. Then we have active elements. Well, if a passive element doesn't add any energy to the system, well, then an active element introduces energy to the system is the opposite. These are the voltage and current sources, right? Those are examples of active elements. These are also, wave generators, right? But that's, I mean, that's just really an AC source, really. Right, so, right, we got passive and active elements. I'm sure, at least, even if you had GEMI, I'm sure you heard of resistors, capacitors, and inductors, okay? Even if that happens, okay? I know, I'm sorry, it's like saying Voldemort.
I'm just having Vietnam flashbacks. Why did you say his name?
He has no power here, guys. He has no power. Okay? It's a safe place. All right, so let's talk about our electrical elements, right? So the resistor. In case you guys forgot, right? Here's what the resistor looks like up here in the top left. And what is a resistor meant to do? What is it meant to do? What does it do? Anybody?
It's the electrical equivalent of a damper.
Yeah, that's true. It is the electrical equivalent to a damper. But what is it designed to do then, Danny?
It reduces current flow based on the applied voltage.
There you go. Hence, right? And that led directly into my next question, which Danny also answered, right? Which is that it acts like a damper, right? Because it dissipates our energy. All right, so we govern these using Ohm's law, right? Where the voltage drop across the resistor is given by the following equation: E sub R, the voltage drop across the resistor. We're going to use E for voltage drop, right? Remember, when we're talking about a voltage drop, we're talking about the net amount of voltage that is lost by crossing that resistor, right? That's why it's called a drop. We have some voltage on one side. When we come out, we will have another amount. How much is that? Well, that's the voltage drop, right? E sub R. So E sub R is really the voltage in minus the voltage out, right? So E sub R is equal to R times I, right? Where E sub R is our voltage drop in volts, I is our current in amps, and R is our resistance in ohms. Right? So this entire equation just uses base units, right? And remember, it's important to keep it in base units because later you can adjust it, right? So how much power is actually dissipated by a resistor? Well, that is given by zeta dot sub R, right? That's negative E sub R times I, which is negative Ri squared, and comes out in watts. Okay. So that's just power through a resistor, right? How much power did you lead off by going through a resistor? All right, so Ohm's law is our ideal linear resistor equation. This is This is our ideal linear resistor equation. So the red box is one of the mathematical truths, right? This is one of our mathematical truths for electrical systems. Okay. Now we'll do a couple of problems later where we see that maybe power and energy come into play, but for the most part, they won't. Right? For the most part, they won't. Okay. So that's a resistor. Right? That's a resistor. You know what? Don't like that. What about a capacitor? What about a capacitor? Well, capacitor is drawn like this here on the right, right? When we see it in our circuit diagrams. Okay. So what's a capacitor supposed to do? What's it designed to do?
Stores charge.
Yeah, stores a charge, right? Stores a charge. Right. It is a capacitor is two conductors separated by a dielectric insulator, right? Which is why we draw it like this, right? We have a conductor on each side, and that middle part that's left blank, right, is supposed to be our dielectric insulator. So we talked about what it does, right? It stores a charge. So what mechanical element is this analogous to? What mechanical element is this analogous to?
Springs.
You would think, right? That's a trap, right? And so
Sorry, that's wrong.
so there is a methodology in which you could say that it is a spring, but that is not the methodology we will be using. We will be using the analogy that a capacitor is like an inertia. And we'll watch a video in a couple minutes that goes through why we're doing it this way.
Yeah, I guess there's two different ways to model electric charge. There's with charge and then current. And current makes more sense because you can use RLC, Kirchhoff's integrated equations.
So our charge voltage relationship for a capacitor, right? We've got some charge that's equal to C E sub C, right? But again, as Danny was saying, right, it's not really convenient to talk about charge, right? Charge isn't something that we typically measure, right? Typically we measure current. So how are current and charge related to one another, right? Well, charge is just the rate of change, or current is just the rate of change of my charge. So Q dot is equal to I. So if I take the derivative of that equation in the line above, right? Again, assuming that my capacitance is constant, I'll just get C E dot C, right? We can calculate the voltage drop if we wanted to, right? But then we have to do some integration. It's not pretty, but it can be done, right? It can be done. It's just the time integration. My energy storage, zeta sub C, is 1/2 C E squared C. So that must mean that our voltage is similar to our velocity, right? Because we've said that this is going to act like an inertia. And if it stores energy like an inertia, then we must be equivocating our voltage and our velocity, right? Because kinetic energy is 1/2 mv squared. Interesting, right? And then we can get power by taking the time derivative of our energy, and we get C E sub C E dot C. Well, that's all well and good, but here's the punchline. Right? Here's the punchline. Notice it's a first order differential equation, right? It's a fundamental capacitor ODE. Q dot is equal to I is equal to C E dot C. And you will notice that I won't even write Q dot from this point on. I'm going to call this I. Current is a much more practical thing to be working with, right? Current is a much more practical thing to be working with. Any questions on resistors or capacitors? No. If you look at well, hopefully with for the homework, you guys use the equation sheet, the master sheet, right? Hopefully that was helpful, but there's all this stuff is tabulated on the master sheet, right? It's all there. All there. All right, and let's talk about inductors, right? So inductors store energy in a magnetic field that's created by current flowing through the inductor, right? And it looks like a spring when you draw it. So it must be analogous to a spring. That's how you remember it. That's how you should remember it, because that is in fact what it is analogous to. For an ideal inductor, we have that our magnetic flux is equal to our inductance times the current through the inductor. Okay. However, we can apply Faraday's law of magnetic induction, which states that a coil of wire will have a voltage difference induced across it if the magnetic flux is changing as a function of time. So therefore, there's some direct relationship between the rate of change of magnetic flux and the voltage, right? So lambda dot is equal to E sub L. So if I take the derivative of lambda is equal to LIL, I take the time derivative of that, I can get that my voltage drop across my inductor is equal to the inductance times the time rate of change of my current. Notice that's a first order ODE too, right? So that's probably going to show up with a red box around it in a second. How do we store energy? Well, we store it like this: 1/2 Li sub L squared. How do we determine energy for a spring? What's the equation for energy in the spring? We didn't explicitly cover it, but do you guys remember digging deep to ESG-360? If you took
KX.
the energy for a spring, not the force.
1/2 kx squared.
Yeah, 1/2 kx squared, right? So in this analogy, if these store energy the same way that springs do, then position and current must be analogous as well here, right? Because we have 1/2 LIL squared. Spring energy is 1/2 kx squared, right? And so those two things must be analogous. Okay. And if we wanted the power, we would take the derivative of that and we would get Li sub L, I dot L, which is just voltage times. Okay, so again, punchline. So what do we have? We've got two elements that are described by first order ordinary differential equations, and we've got one element that is described by just a straight linear relationship, right? So electrical systems are a little bit different because every time you have an energy storage element like a capacitor or an inductor, right? Anytime you have one of those, you add an order to your system, right? So a circuit so an RLC circuit, because it has a single inductor and a single capacitor, is a second order system. So these things, the more components you add, the higher the order becomes, right? So you could see where in real life, these systems get really high order really quickly, right? In the case of, so I will say it now and I'll say it again when we get to some examples, but I would highly recommend writing an equation for each of your energy storage elements, right? Because remember, if you have a second order system, you're going to need two equations if you're using first order ODEs. You guys have any questions on elements right now? No? Not really? Tracking okay? Okay. Let's watch a video about how inductors work.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at inductors to learn how they work, where we use them and why they're important. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. So what is an inductor? An inductor is a component in an electrical circuit which stores energy in its magnetic field. It can release this energy almost instantly, and we'll see how it does that later on in this video. Being able to store and quickly release energy is a very important feature, and that's why we're going to use these in all sorts of circuits. Now, in our previous video, we looked at how capacitors work. Do check that out if you haven't already, links down below. So how does an inductor work? I want you to first think about water flowing through some pipes. There is a pump which pushes this water, and the pump is equivalent to our battery in the circuit. The pipe will split into two branches, and the pipes are equivalent to our wires. One branch has a pipe with a reducer in it, and that reduction makes it a little harder for water to flow through it. So the reducer is equivalent to resistance in our electrical circuit. The other branch has a water wheel built into it. The water wheel can rotate, and the water flowing through it will cause it to rotate. The wheel is very heavy though, so it takes some time to get it up to speed, and the water has to keep pushing against this to get it to move. This water wheel is going to be equivalent to our inductor. When we first start the pump, the water is going to flow, and it wants to get back to the pump as this is a closed loop. This is just like when electrons leave the battery, they flow and try and get back to the other side of the battery. By the way, in these animations I use electron flow, which is from negative to positive, but you might be used to seeing conventional flow, which is from positive to negative. Just be aware of the two and which one we're using. So as the water flows, it reaches the branches and has to now decide which path to take. The water pushes against the wheel, but the wheel is going to take some time to get moving, and so it's adding a lot of resistance to the pipe, making it too difficult for the water to flow through this path. Therefore, the water will instead take the path of the reducer because it can flow straight through this and get back to the pump much easier. As the water keeps pushing, the wheel will begin to turn faster and faster until it reaches its maximum speed. Now, the wheel doesn't provide almost any resistance, so the water can flow through this path much easier than the path with the reducer in it. The water will pretty much stop flowing through the reducer, and it will all now flow through the water wheel. When we turn off the pump, no more water will enter the system, but the water wheel is going so fast it can't just stop, it has inertia. As it keeps rotating, it will now push the water and act like a pump. The water will flow around the loop back on itself until the resistance in the pipes and the reducer slows the water down enough that the wheel stops spinning. We can therefore turn the pump on and off, and the water wheel will keep the water moving for a short duration during these interruptions. We get a very similar scenario when we connect an inductor in parallel with a resistive load such as a lamp. This is the same circuit as we just saw, but I've just wired it more neatly. When we power the circuit, the electrons are going to first flow through the lamp and power it. Very little current will flow through the inductor because of its resistance at first is too large. The resistance will reduce and allow more current to flow. Eventually, the inductor provides nearly no resistance, and so the electrons will prefer to take this path back to the power source rather than through the lamp, so the lamp will turn off. When we disconnect the power supply, the inductor is going to continue pushing electrons around in a loop and through the lamp until the resistance dissipates the energy. So what's happening in the inductor for it to act like this? Well, when we pass electrical current through a wire, the wire will generate a magnetic field around it. We can actually see this magnetic field by placing compasses around the wire. When we pass a current through the wire, the compasses will move and align with the magnetic field. When we reverse the direction of the current, the magnetic field reverses, and so the compasses will also reverse direction to align with this. The more current we pass through the wire, the larger the magnetic field becomes. When we wrap the wire into a coil, each wire again produces a magnetic field, but now it will all merge together and form one large, more powerful magnetic field. We can see the magnetic field of a magnet just by sprinkling some iron filings over the magnet, which will reveal the magnetic flux lines. When the electricity supply is off, no magnetic field exists. But when we connect the power supply, current will begin to flow through the coil, so a magnetic field will begin to form and increase in size up to its maximum. The magnetic field is storing energy. When the power is cut, the magnetic field will begin to collapse, and so the magnetic field will be converted into electrical energy, and this pushes the electrons along. In reality, it's going to happen incredibly fast. I've just slowed these animations down to make it easier to see and understand. So why does it do this? Well, inductors don't like changing current. They want everything to remain the same. When the current increases, they try to stop it with an opposing force. When the current decreases, they try to stop it by pushing electrons out to try and keep it the way it was. So when the circuit goes from off to on, there will be a change in current. It has increased. The inductor is going to try to stop this, and so it creates an opposing force known as a back EMF, or an electromotive force. This back EMF opposes the force which created it. In this case, that's the current flowing through the inductor from the battery. Some current is still going to flow through though, and as it does, it generates a magnetic field which will gradually increase. As it increases, more and more current will flow through the inductor, and the back EMF will eventually fade away. The magnetic field will reach its maximum and the current stabilizes. The inductor no longer resists the flow of current and acts like a normal piece of wire. This creates a very easy path for the electrons to flow back to the battery, much easier than flowing through the lamp. So the electrons will flow through the inductor and the lamp will no longer shine. When we cut the power, the inductor realizes that there has been a reduction in current. It doesn't like this and tries to keep it constant. So it's going to push electrons out and try to stabilize it. This will power the light up. Remember, the magnetic field has stored energy from the electrons flowing through it, and it will convert this back into electrical energy to try and stabilize the current flow. But the magnetic field will only exist when the current passes through the wire, and so as the current decreases from the resistance of the circuit, the magnetic field collapses until it no longer provides any power. If we connected a resistor and an inductor in separate circuits to an oscilloscope, then we can visually see the effects. When no current flows, the line is constant and flat at zero. But when we pass current through the resistor, we get an instant vertical plot straight up, and then the flat line continues at a certain value. But when we connect an inductor and pass current through it, it will not instantly rise up. It will gradually increase and form a curved profile, eventually continuing at a flat rate. When we stop the current flowing through the resistor, it again instantly drops and we get this sudden vertical line back down to zero. But when we stop the current through the inductor, the current continues and we get another curved profile down to zero. This shows us how the inductor resists the initial increase and also tries to prevent the decrease. By the way, we've covered electrical current in detail in a previous video. Do check that out, links down below. What do inductors look like? Inductors in circuit boards will look something like this. Basically just some copper wire wrapped around a cylinder or a ring. We do get some other designs which have some casing over. This casing is usually to shield the magnetic field and prevent this from interfering with other components. We will see inductors represented on engineering drawings with symbols like these. Something to remember is that everything with a coiled wire will act as an inductor. That includes motors, transformers and relays. So what do we use inductors for? We use them in boost converters to increase the DC output voltage while decreasing the current. We can use them to choke an AC supply and only allow DC to pass. We can use them to filter and separate different frequencies. And obviously we also use them for transformers, motors and relays. How do we measure inductance? We measure the inductance of an inductor in the unit of Henry with a capital H. The larger the number, the higher the inductance. The higher the inductance, the more energy we can store and provide. It will also take longer for the magnetic field to build and the back EMF will take longer to overcome. You can't measure inductance with a standard multimeter, although you can get some models with this function built in, but it won't give you the most accurate results. That might be okay for you, it depends what you're using it for. To measure inductance accurately, we need to use an RLC meter. We simply connect the inductor to the unit and it will run a quick test to measure the values. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now.
All right. So those are inductors. Inductors are everywhere, and we'll see later, probably Thursday, that inductors are basically the reason that we have electromechanical systems. Right? They allow us to couple between electrical and mechanical systems. All right, so this cartoon, right? Resistance, no, I'm not going to have any cake, right? Inductance, we'll store the cake for later, right? But capacitance has all of the cake, okay? Stores all of the cake. That's also, I like this one. I know it's on the, it was on a previous slide, but I like the idea of resistance being a wrangler of current. And voltage is pushing, right? And we're restricting, our resistance is restricting the amperage that's coming through. All right, so those are our passive elements, right? And as I said earlier in class, we have active elements as well, right? It's a little bit different. I guess you could consider this to be like a force source, right, in a mechanical system, but we typically have voltage or a current source. Now, an ideal voltage source provides a specified input voltage regardless of the amount of current that it needs to draw, right? So again, it's ideal. So if it's an ideal voltage source that provides 10 volts, you will always have 10 volts. Doesn't matter how much current you need, right? You'll always be at 10 volts. Likewise, an ideal current source will always provide you with the amount of current that it says that it is providing, regardless of the amount of voltage that might be required to produce said current. Okay. The arrow symbol in the current source denotes a positive convention for current flow, right? So, right, think about this as flowing up, right? It's flowing up. That's what the arrow means. Will you ever see one that's pointed down? Maybe, maybe not. You should never see one that's pointed sideways because that wouldn't make any sense in this situation, right? There's no wires coming out to the side. So there's that. Has to be pointed in the direction of the wire. It has to be pointed in the direction of the wire. Okay. So let's watch a video where we talk about where we can see these analogies. Now, before we watch this, I want to say that what they're doing in the video is not something that I expect you guys to be able to do, but it is one of the applications of using dynamic system approach to solving problems, right? So where do our analogies come from, right? We've obviously seen that they're not what we thought they would be, right? Because we thought a capacitor should be, or I'm sorry, we thought that a spring should be a capacitor, right? So what's the deal?
It's possible when talking about mechanical systems and electronic circuits to develop analogs between them. So if you remember, across variables, such as velocity and voltage, can be related with through variables, force and current, through various variables. And we have differential equations that allow us to turn cross variables into through variables. So also remember that the dynamical system has a behavior that's described by its equation.
Oh, shoot, sorry. Technical difficulties.
It's possible when talking about mechanical systems and electronic circuits to develop analogs, and we have differential equations that allow us to turn cross variables into through variables. So also remember that
Oh my gosh, really? Okay. There.
the dynamical system has to obey the differential equation, the ODE that describes it. So that's the equation of motion. So here's an idea. Let's say that we have some equation of motion, and we have it for a dynamical system, well, a mechanical system. So what circuit would have the equivalent equations of motion? So this would be an interesting way to see whether you really understand what the fundamental topics are. But I have to warn you, some of the analogies that are made are not that easy to understand. So you have to go to the math first, and then move from the math to your deep understanding. So let's begin with a couple of atomic examples. So the very first one that I'm going to have is a force that pushes on this mass m1, and we've indicated direction of motion here with x1. So you may remember that we have F as m1 x1 double dot. So force is mass times acceleration here because direction of motion is indicated by x1. Direction of acceleration is x1 double dot. So this is an extremely simple example. But clearly, if you kept pushing with this force and there was no resistance, eventually the mass would be going really fast, right? And eventually it would, do things that it's not supposed to do. So we can also rewrite this as m1 v1 dot instead of x1 double dot. Because v1, of course, is x1 dot. So v1 dot is x1 double dot. So now let's go into the twilight zone. Here we're going to actually talk about circuits using the same kinds of variables. So the first equation that I want to write is I is equal to mass times the rate of change in time of voltage. So I've used force as a through variable, and now I've mapped that to current as a through variable. We began with velocity as an across variable, and now we have voltage as an across variable. So what does this look like as a circuit? Well, we already have a circuit component that obeys the law of I equals something times voltage with respect to time. And that's a capacitor. So if we imagine that the mass acts like a capacitor here, then what we get is that the analogous circuit to this dynamical physical system is just a capacitor mapped in parallel with a current source. So clearly, you would never turn on this current source and leave it on with a physical device, right? Eventually that capacitor would explode and you would see a capacitor juice all over the place. So the same thing is true with a mass on the left. If you kept pushing with the same force, you would eventually see something really bad happen. So either the mass will be going so fast it'll start to violate all kinds of laws and you'll get pulled over by the cops, or of course eventually in an ideal world you'd be exceeding the speed of light, which is not allowed either. So this is the very first example. So the mass acts like a capacitance. Let's look at a second example. So now I have a mass, and I'm attaching that mass to a spring. So the spring has some constant K1. So let's first talk about what are the ordinary differential equations that map here. So if we have F is the sum of all forces, so here m1 x1 double dot plus k1 x1. So when we push with this force, that's equivalent to the inertial motion in the same direction plus k1 x1. So we can rewrite this as m1 v1 dot plus k1 integral v1 dt. So I've taken x1 and taken its integral so that I can write it as v1. So we can rewrite this as a current source, I, with the capacitor, m1. And what is K1 times the integral of voltage? Well, we already know that voltage is, across an inductor, is L times the derivative of the current. So we can integrate the voltage to get L times I, and divide through by L to get an equation for I in terms of voltage. So now we can see that the spring actually acts like an inductor. So the first current comes out of this node and drives south through M1. The second current also comes out of the same node and drives through the inductor. So here we have the mass acting like a capacitor and the spring acting like an inductor. Let's look at the third case. So now I'm not using a spring, I'm using a damper. So the damper has some physical coefficient B1. So F again is equal to M1 x1 double dot plus B1 x1 dot. And so we can rewrite this in terms of V, M1 V1 dot plus B1 V1. So now if we push with this force, first of all inertia pushes back, and then second of all this damper is going to push back. So let's go into the twilight zone again. Now we have a current source I. We have our mass M1 V1 dot, so that's the capacitance. But again, now we're looking at how do we dissipate energy based just on the velocity, or just on the voltage. And we actually know how to do that with a resistor. So B1 V1, but we can't just choose B1 as the value of the resistor, because voltage is a current times a resistance. And therefore the current is equal to 1 over the resistance times the voltage. So if our resistance is 1 over R, but the value in front of V1 is B1, then our resistor's value must be 1 over B1. So even though the spring acts like an inductor, we have to invert it to get the inductor's constant. And even though the dash pot, or the damper, acts like a resistor, we have to invert its value to get its resistance. So this is how we come up with, fundamentally, from its atomic pieces, how a circuit would be analogous to a physical system. So let's look at an example from the text. This is an example where you can find this diagram and its analogous circuit. So here we have a mass, M1. We're pulling on it with some force R of t. And then M1 is connected to two dash pots, and one of those dash pots has a mass and another spring in series with it. So we indicate velocity in this direction. And we remember that the sum of all forces is mass times acceleration. So M1 V1 dot, that's the direction downward, right? So we expect that R, which is our force, will be positive on the right-hand side. But then we're going to have negative values that are preventing us from doing that based on these two dash pots. So B2 V1 is going to be pointing in the opposite direction, it's negative. And B1 times V1 minus V2 is also negative, so it's pointing upward. Our second equation, based just on M2, means that we take just the dash pot times V1 minus V2, and then we subtract away the value of the spring. So as V2 moves down, we're expecting that we're going to get a force pulling up. So that's why that value is negative, whereas the B1 value is positive, because we wrote V1 minus V2 instead of V2 minus V1. If this doesn't make sense to you, you can go back and look at the diagrams that we did just on dash pots and just on springs to show how these values can be decomposed. So now we can rewrite this in terms of x1 and x2, obviously. And this is just a change of variables. So some have more dots and some have fewer dots now. But I'm staying with the v's for a reason that will become clear soon. So now I want to isolate the force and put it all on one side of the equation. So once you do that, you can come up with this rewriting. So now we have some current equal to pieces on the right, and then we have the sum of a bunch of other forces being equal to 0. So now we're going to rewrite this so that we'll have it on this page. And I want to consider for just a second that we're actually treating V not as velocity, but as voltage. So we did this with the atomic examples. Now I want to do it with a slightly more complicated example to show how these pieces compose. And R is going to be our current. So V1 dot is dV1 dt, or M1 times V1 dot is going to be some kind of a capacitance, C dV dt. The integral of V2 dt is the same, or is analogous to 1 over L times V2 dt, which is some current, because we know that V is L di dt. So now, again, we see that the mass acts like a capacitance, and that the K is the inverse to an inductance. So if we have K times the integral V2 dt, which we see up there in equation 2, that's 1 over L integral V2 dt. So our inductor's value, that is, what's the value for our inductor, is 1 over K. Because 1 over K is K. So for just a regular resistance, B times the voltage is 1 over the resistance of the voltage. So this gives us the analogous of what our currents are equal to. So in this case, again, we have dashpots that act a little bit like resistances, but this damper is actually inverse to a resistance. So because you have a damper, it acts like a resistance, but the value of that resistor is the inverse value of the damper. That is, R1 is equal to 1 over B1. Okay, so let's rewrite these equations again so that we have them. And now let's draw our circuit. So R is going to be the sum of a bunch of different forces. And so if we use KCL, then the sum of all the currents has to be equal to 0. So if we draw R going into this node and the other currents going out of the node, then R will be on the left-hand side and the other currents will be on the right-hand side. So the first current that comes out, M1 V1 dot, well, we use the mass M1 and we label that this node is V1 because the current through a capacitor is C dV dt. So here the value for C is M1 and the value for V is V1. So we have to decompose just a little bit some of these other pieces to find out that this second current is B2 times V1. And so in fact the value of the resistance is 1 over B2. We also have V1 minus V2. all multiplied by B1. So you can see in the equation 1, we have B1 plus B2 times V1, right? But when we translate that into the circuit, we're interested in the original resistor values. And so we're going to have one current attributed to the resistor B2, and we're going to have another current attributed to the resistance for B1. And so now we're actually going to make this resistor value 1 over B1 here, but we need to create another node V2 because we're interested in the potential V1 minus V2. So that second resistance here divides its current, and we'll see that in just a moment. So this current coming out of V2 will be divided in two ways. So one of the ways that the current in V2 is divided is that it goes through this capacitance M2. And then the other way that the current is divided is that we're interested in the current through the inductor. So K times the integral V2 dt. And remember that K here should be inverted.
All right, so I'm gonna stop it there, right? Because I can't. I feel like you guys are mostly glazing on me right now. So what is the point, right? What is the point? Why show you all of this? Well, this is powerful, right? This is powerful, right? Because what is this saying? If this circuit is equivalent to that mechanical system, if those two things are equivalent, why is this powerful? Well, if they're equivalent, they should have the same response, right? So, say you design a mechanical system and you don't have the money to prototype it, but you've got a bunch of spare resistors and inductors and capacitors lying around and some breadboards. You could simulate the response of your mechanical system using a circuit, right? Because if they're equivalent, then the response should be the same, right? And that's the power of doing this, right? These things are, if they're all equivalent, it doesn't matter how I solve them, right? It doesn't matter if I use my fancy mechanical system 5 steps that I used before, if I use my analogous circuit, right? The response, the differential equation isn't changing. We're just changing the variables, right? And that's the point. And the way that we get from there to here is by treating our variables in this way. Okay? Again, I'm not expecting you guys to be able to create equivalent circuits from mechanical systems. Not the point of this. The point is to show you that this can extend across engineering disciplines, right? And can be a very powerful analysis tool once we get there. Is there any questions on electrical elements so far? We doing okay? Now I understand that you guys have a lot of scar tissue with this subject. I get it, okay? Don't let that get in the way. All right, try to approach it with an open mind, okay? We're really not going to do anything beyond Kirchhoff's laws here, okay? We're not. Any questions so far? Everybody okay? Maybe, maybe not. Okay. All right then. So what's an electrical system then? All right, so before we get into this, when I ask questions like what is an electrical system, right? Please don't say it is a system that uses electricity. Okay, don't just rearrange the words in the definition. That's not really defining something. Right? But anyway, so what is an electrical system? What is it created to do, right? Well, it's created to take some sort of electrical energy and store it, or store it or dissipate it or discharge it at certain intervals, right? So for electrical systems, the important dynamic variables that we're going to talk about are current and voltage, right? E and I, voltage and current. You are going to want to have all of your equations. We're going to simplify this down. All of your equations need to be in terms of E or I. I don't want to see any other dynamic variables in there. The only dynamic variables that exist in this class are voltage and current, all right? That is it. Furthermore, the energy stored by a capacitor and an inductor depends on the capacitor voltage and the inductor current. We are not going to do any of the funky integral signs on our, right? We're going to have everything in terms of I or I dot, nothing in terms of integrals right now, okay? It's just cleaner. It's just cleaner, right? We already went over the fundamental ODEs that describe capacitors and inductors, right? But a mathematical model of electrical systems can be written in terms of E sub C and I sub L. Okay. If the variables that you have in your equation aren't E sub C or I sub L, you need to figure out how to make them E sub C and I sub L. And we'll see what we're talking about in a minute. And the voltages and currents in an electrical circuit that are not E sub L, we can talk about that, need to be written in terms of the important dynamic variables using Kirchhoff's laws, right? So we're simplifying it. There's only really two dynamic variables that we're interested in, E sub C and I sub L. The voltage drop across my capacitor and the current through my inductor, right? Everything else needs to be, if you have a current through a resistor, you need to make it look, you need to write it in terms of either a current through an inductor or the voltage drop across a capacitor, right? That's what we're doing. So how do we get there? Well, we said we're going to use Kirchhoff's laws. For those of us that don't remember, let's talk a little bit about Kirchhoff's laws, right? We've got Kirchhoff's voltage and current laws. We'll start with the KVL, Kirchhoff's voltage law. What does Kirchhoff's voltage law say? Well, it says that the voltage drop, the sum of the voltage drops around a closed loop equals 0. So for example, let's look at this circuit that we have over here, right? If I start with E in, well, E in minus E1 minus E2 minus E3 has to equal 0. Another way of saying this is that, right, another way of phrasing this is that E in of T is equal to E1 plus E2 plus E3. So the amount of voltage that I put in has to equal the amount of voltage that is dissipated as I travel through my loop, right? That is what it's saying. All right, so there's sign convention that we talk about here, right? Moving across a passive element from positive to negative in the direction of current flow, or moving across a voltage source from positive to negative is a voltage drop, right? So if we're moving across our element 1 here, right? So our current would be, we're going to say it's flowing this way, right? This is I, right? So this is a voltage drop, right? That's a drop. We also have a drop here. So how do we signify a drop? Well, drop is subtracted, right? We have some total current. So let's think about this, right? Let's think about this. If that's my voltage drop, right? How much current do I have coming into element 1? Or I'm sorry, how much voltage do I have coming into element 1, right? Well, I have E in, right? Everybody's cool with that, right? I had E in to start with. I didn't hit any elements until I got here. So I still have E in here. We're talking about an ideal world. I understand that in the real world, wires have resistance. We're not talking about that, right? We're assuming ideally what will happen, right? So we have E in on this side, right? Experience some drop. What are we left with on the other side? Well, this, right, has to be E in minus E1, right? Over here. Right? Because we know the voltage drop across that is E1. That's how much we're changing by. That's how much we're changing by. That's what we're left with is E in minus E1. All right. So now we have E in minus E1 going through element 2, right? And my current is still flowing this way. Right? My current hasn't changed yet. These are all in series, so my current hasn't had to divide or anything. So that's I. Okay, well, what comes out on this side? Well, on this side, we're going to have E in minus E1 minus E2. Right? Again, current still flowing this way. It's still I. When we come out on this side, we got E in minus E1 minus E2 minus Kirchhoff's voltage law. Right? What if we were running our current in the opposite direction? Good question, right? What if? Well, if you run your current across a passive element from negative to positive, that is not a voltage drop, right? That's going to be a voltage gain. So essentially, if you run it in the reverse direction, you flip your signs, right? You run it in the reverse direction, you flip your signs. So if you're going from negative to positive, right, that is a voltage gain or voltage rise. And if you're going from positive to negative, that's going to be a voltage drop. Okay? Everybody cool with the KVL, right? Because the way KVL is basically, we're going to use it kind of like Newton's law for these types of equations. Like KVL and KCL get used like Newton's laws here. Any questions on KVL? Are we okay with it? So let's talk about KCL. What is KCL? Well, it's Kirchhoff's current law, right? And what does Kirchhoff's current law tell us? It tells us that the algebraic sum of the currents entering and leaving a node is equal to 0. Another way of thinking about this is that all of the stuff entering a node has to equal all of the stuff leaving the node, right? So the sum of my current into this node, like we'll call this node here, we'll call it A, because I'm not creative enough to come up with a sweet variable on the fly. So A is the one we're going with, right? So if we were doing the current law here, what would we say? Well, we would say that, you know, I1 plus I4 is equal to I2 plus I3, or you could say that I1 plus I4 minus I2 minus I3 is equal to 0, right? Like how it's written. When do we use the current law versus the voltage law, right? When do we do that? Well, let's define what a node is first, right? A node is a junction that has 3 or more wires coming from it, right? So if we go back to our previous statement here, or a previous slide, this circuit has no junctions, right? It has no junctions. If you don't have a junction, you cannot apply KCL. Or, I mean, you could, right? But like, so for example, if I put a node here, right? Well, all of the current going in has to equal all the current coming out at A, right? Well, I mean, there's only one thing going in, one thing going out, so the current doesn't change, right? So you can apply a trivial KCL. Typically, we will do it at any time that we have a node that has 3 or more wires associated with it. Okay. You guys have any questions on KVL, KCL? No? Okay. Okie dokies. So how do we model these things, right? We talked about it a little. But how do we actually model these? So here it goes. All right. The book would tell you that you can use a systematic 2-step process for creating mathematical models of electrical systems. I will tell you that they are a liar, because you should use the 5-step method that we came up with. Why? Because it has more steps, so obviously it's better, right? Because this is only 2 steps, the other one has 5 steps, so that makes it better, and it's 3 better. Right? That's how math works. The important thing here is that all ODEs should be solely in terms of E sub C, I sub L, E in, or I in, right? We should not have anything that is not within these 4 variables in our models. We're going to use Kirchhoff's laws to express unknown voltages in terms of our dynamic variables, right? Okay, so these 2 steps are included in this, right? So we'll do this again. We'll walk through it again, right? So we're going to draw a picture. In this case, we need a circuit diagram, right? You want an annotated circuit diagram, right? Why? Well, because if you have an annotated circuit diagram that's good enough, you can do KCL and KVL by looking at it, right? And you shouldn't have any issues there. Right? Then we identify our inputs and outputs. That's the same thing, right? It's a little bit easier in electrical systems to determine the input because you have a source, right? Your inputs have to come from sources. What's our output? Well, I told you our outputs for this are going to be E sub C or I sub L. How do you know which one to use and when? Well, if you have a capacitor, you need one in terms of E sub C. If you have an inductor, you need one in terms of I sub L. And if you have both a capacitor and an inductor, then you need to have one equation for each of those energy storage elements because these are all first order ODEs, right? And in order to encapsulate the entire order of the system, we need to have one equation for each of our energy storage elements. Okay. Write our statements of relative physical truth. What are those? We have our element equations, right? We've got Ohm's law. We've got I sub C is equal to E, C E dot C, and E sub L is equal to L I dot L. We've got our current and voltage laws. Those are the truths that we're going to be dealing with. Then we reduce our equations, right? So we're going to make our input-output equations from there, right? And then we're not evaluating yet, but we're as the pendulum of time swings, we slowly approach that time. All right, so here we are. So let's walk through one, right? This is a fairly simple example. Question: what order system do you guys think that this is? What order system?
Second order system if considered for current.
Second order? Is it second order? How many energy storages do I have in here?
1.
One.
That's our
I have one ODE. Remember, the resistance is described by Ohm's law, which is not an ODE. This is going to be a first order mechanical system. First order, electrical, not mechanical. It's obviously not mechanical. So we've got our simple RL circuit. So let's start with our circuit diagram, right? Well, we had one on the previous page, but I will redraw it. And so I've got some E in, which is a function of time here, plus and minus. I've got my inductor. I've got my resistor, and I'm going to say that we were shown that the current loops this way, right? It's my I sub L. Another way, if you don't like to draw it that way, another way you could do this is say do I sub L, right? Just so you know which way the current is flowing. All right, so based on what we talked about so far in class today, what is my input for this system? What's my input?
EN.
E in. Excellent. Excellent. So E in is my input. What about my output? What should my output
EN.
No, I mean, it's the input, right? So let's look at it, right? Remember what I said, right? All of our equations. So all right, let's think about this, right? We have one energy storage element. I need everything in terms of how I'm storing the energy, right? I have one ODE. What is that ODE a function of, right? Well, let's back up from there, right? couple slides ago, and I'm going to bring it back. A couple slides ago, for that one. All ODEs should be solely in terms of E sub C, I sub L, E in, or I in. Which element do we have that stores energy in this circuit?
I sub L.
It's going to be I sub L, right? We are going to have an output of inductor current, right? Call this I sub L. So look at our mathematical truths here, right? And so I've got, for an inductor, I've got L I dot L is equal to E sub L, right? So this is the first order ODE that describes my voltage drop across my inductor. I also have a resistor, which is equal to I. Well, I'm going to write it this way, RIR. Okay. All right, so let's look back at our diagram again, right? And my question to you guys is, do I need to use the current loop or the voltage loop as my main equation here?
Voltage loop.
All right, the voltage loop, right? And we'll assume that our voltage loop moves in the direction of current, right? So I'll say, this is going to be my KVL loop here, just for notes purposes, right? This is going to be positive and negative. This is going to be positive and negative, right? So, all right, so we need KVL, right? So what does KVL tell us here? What does KVL tell us here? So we'll write KVL as one of our truths, right? Well, if we're moving in that direction, right, I've got E sub n as a function of time, minus E sub L, minus E sub R is equal to 0, right? Remember, we'll go back to the diagram again. Remember, if we're traveling in this direction that I've drawn by the green arrow, we are traveling in the same direction as the current, right? That means that I have a voltage drop across my inductor, and I have a voltage drop across my resistor, right? And I'm putting in E sub n. So E sub n minus E sub L minus E sub R is equal to 0, because this is a closed loop. Okay. How much current do I have over here, where I just drew the current coming out of the inductor going into the resistor? How much current is that?
Same as IL.
It's IL, right? It hasn't hit a node, it hasn't split, right? So if you really wanted to, right, you could do KCL at this node, right? But KCL at the node is just going to tell you that IL, right? If I called, so let's, if you really wanted to, right? You say, well, I'm going to call this IR because I know I have that much current across through my resistor. Or, well, this would tell me that at A, IL is equal to IR, right? Everything going in has to be coming out. So this is just equal to IL, which is actually one of my truths, right? IR is equal to IL. And that's going to be important in a second when we do our reduction. Okay. All right, is everybody okay up through the mathematical truths at this point? I know it's switching gears a little bit, and we're not all familiar with all the elements and stuff right now. Is everybody following? Everybody feeling okay with stuff so far?
What'd you say the output was?
I sub L. For electrical systems, we're always going to have an output of I sub L or E sub C. Those are the only two outputs that exist for this class. Could you have other things? Sure. For this class, don't write anything other than I sub L or E sub C as your outputs. Also, don't put like EN as an output. That's clearly an input. It even tells you that it's an input, right? That's like, it's a softball, man. Don't miss that one. Don't miss that one.
So would we need to expand, I guess, E sub L, E sub R at all? Or given that those are pretty static, would we just be able to keep those as, I
We're gonna
guess,
keep them,
that
Sean,
form?
law still, right? But we need to massage it so that we get it in terms of E sub L or I sub L or E sub C, right? That's what's going to happen. So we're going to do some algebra, right, in our reduction. So we're going to start with our KVL equation. I'm just going to rearrange it a little bit, right? That's E sub L is equal to E in minus E sub R. Okay? I'm going to rewrite it like that. Okay? Remember, we're going to keep E in as is, right? We can keep that's our input. E in's going to stay. We're not touching that. But I can make some substitutions here because E sub L is equal to L I dot L. And this is equal to R I sub R. But we also wrote that, right, so from here, we need to get I sub R in terms of our output, right? Or our input, whichever one we want. Well, this is easy, right? Because we know that I sub R is equal to I sub L. No, I dot L plus R I sub L is equal to E. First order system gets one equation. It's done. So our input has to equal, the voltage input has to equal this, right? Has to equal this. So here's the thing. Here's the thing. Most of the time, we are going to be spending with these models is going to be figuring out how to make our variables align in terms of our inputs and our outputs. And again, this is going to be one of those things where for right now, you're going to be like, Dr. D, I don't understand why you're being such a hard ass about inputs and outputs, right? And I get that. Please trust
Dr. D.
that this is going to be helpful when we get a little bit further on in class. Yeah, what's up?
How did the I sub R switch to E I sub L?
Yes. Well, let's go back to our diagram. So how is the current affected by flowing through an inductor? Right? It's not. Right? We have an ideal amount of current. So the only time that our current will split, right? So another way of drawing this, right? Instead of me doing that, right? I know that I have some current through here, right? Through some current through my inductor. Yes, we're going to call that I sub L. Right? If I wanted to do KCL at this node A, which is not a node, right? But this bisection, this intersection, let's call it, right? If you were to do Kirchhoff's current law there, what would you get? You get that I sub L has to equal I sub R, right? Because there's only one thing coming in and one thing coming out. And that's where it comes from. Remember, the current in an electrical system, the current only changes if we branch, right? If we hit, right? So in this case, if I had another wire coming here, this is no longer true, right? Because you have something else coming out. But for this type of system where we have a single closed loop, right? Where everything is in series, the amount of current that passes through each element is the same. Okay. Now, there's going to be cases which we will see in a second Boy, that is not what happens. Let's say that that's from a trivial. So when I say that it's trivial, it's just because there's only one thing coming in and one thing going out, right? It's a trivial thing. Okay. Any other questions? Okay, so that's gonna be basically, that's basically the simplest thing, right? That's the simplest circuit that we're looking at, RL or an RC circuit. Right? Those are gonna be the simplest ones we can analyze. So I want you guys to take a few minutes. I'll throw you into your groups for this one. Why not? You guys can work together as groups, not for tri-quizzer points, just to work on it. Why don't we say, I'll give you guys 20 minutes to work on this and we'll see how far we get. All right, I'll bounce around. I think we've got everybody. I'll set this for 20, perfect. All right, so copy that down. Give you a couple of seconds to copy it down and then I'll open up the rooms. All right. And so this is the circuit, right? It's got a current input. You've got, it's already telling you that you've got a node A, right? This is a parallel circuit. That's being told a lot from this drawing. Another minute or another couple of seconds to draw it down and take a screenshot, and then I will throw you into groups. All right, opening up the rooms.
Hey, Professor.
What's up?
I had a question. Did two of our classmates end up switching classes or something, or have
I
they just
believe
not been?
so. It looks that way. So what I'll probably do is, let's see, which, yeah. So I've got to figure that I might switch. I might split you guys to two other teams of three.
Okay.
But not today.
All right. Sounds good. Thank you.
Yep. All right. So we're back. Sorry if I didn't get to your room. I got to be faster or moving around. I apologize. But here we are, right? So here's our circuit diagram, right? And this one's pretty well annotated. So I am going to redraw it, right? Why? Because there's a couple of things that I want to add here, okay? There's a couple of things. And this one, right, really kind of tried to pull on your knowledge of circuits from the past. And I know you're all dead on the inside from circuits class. I know, I get it. Okay? You need to move on. Okay, so remember, Kirchhoff's law says that as long as we have a closed loop, the voltage drop totals 0 in that closed loop. It doesn't matter where that closed loop is. It is any closed loop, right? Any closed loop. So we have one here on the left-hand side. We've got one here on the right-hand side. We even have one if we wanted to go the entire perimeter around, right? But that makes our drawing not look nice, so I'm going to get rid of it. Okay? But you could follow all the way around the edge, right? And that would be there, right? And I'm also just going to write this so I remember that this actually flowing into A is I in, right? And the book that I pulled this from originally was nice enough, right? Was nice enough to put a node for us at A already, right? So we know that there is a node at A, right? So what about our inputs and our outputs? Well, what's our input, right? Everybody all together, our input is
IN.
IN. Exactly. Don't miss the ends. Right? Don't miss the ends. What about our output? What's our output going to be?
EC. E sub C.
Yep. You see, does there exist a world in which we can use current as the output? Yes, there does. There exists a world in which we could do that. And as I said to some of you, that world is a dark place in which we need to do integration, right? And I know we pull our blankets around us tighter when we hear the word. So we're not going to go into that world. That's why I'm limiting this here, right? E sub C and I sub L. Right? We're just going to focus on taking derivatives for these systems, not on integrating them, right? So what are our mathematical truths? Well, for a resistor, E sub R in general is RIR, and for a capacitor, I sub C is equal to C E dot C I sub R. Okay. We're going to take the KCL at node A, right? And KCL at node A tells us what? It tells us that I in of time is equal to I sub C minus I sub 2, right? Let's go back. For a second. Right, so I've got I in flowing in. I've got I sub C across both of these components, both of these elements, and I've got I2 up here, right? Remember, this is stemming from A, right? So that's what I have. So IN is equal to IC plus I2. And that's great. That's great. But, right, and I wrote this for the general case, so why don't I be a little bit more specific here, right? So ER1 is equal to R1 IC, right? And ER2 is equal to R2 I2. Now here's the problem from looking at these, right? Here's straight up the problem. I sub C is just equal to this. So that's a quick input, and I have something in terms of E dot C right away, right? I2 is not related to E sub C at all yet. So how do we get it there? Well, I'm going to use KVL. Now, if we go back to our diagram, which one of these loops, right, left-hand side or right-hand side, which one of these loops couples R2 and C. Which one of these loops will allow me to write an expression for that voltage drop across the resistor in terms of the voltage drop across the capacitor? Which one?
Right-hand side.
Right-hand side, right? This side has all of the interesting elements. This side wouldn't gain us. We wouldn't gain anything from doing a KVL on this side, right? We wouldn't. So let's use our KVL, the right-hand side, right? And I'm going to go back and I'm going to draw some things on this diagram, right? Because they're going to be helpful. Remember, positive, negative, positive, negative, positive, negative, right? And if I'm going in this direction as I've drawn, right, that means what? Well, I'm going to have negative ER2 plus EC plus ER1 is equal to 0, right? Because remember, now I'm following the direction of the green arrow here, right? This rotation. And if I start at A, well, I'm going to have a voltage drop across R, but then we're going to come back up this branch. And now this is a voltage gain across the capacitor, and this is a voltage gain across R, right? Because we're in the opposite direction of our convention. So when we write this, we'll end up with negative ER2 plus EC plus ER1. And those are the truths, right? Now, okay, is everybody okay with this, right? Remember, it's okay to split this up, right? It's okay to split up KVL. The only thing that we need to remember for KVL is that whatever we're analyzing with our voltage law has to be in a closed loop. It doesn't matter where that closed loop is. It's just the fact that it's a closed loop. Any closed loop. Any closed loop. So the question always comes up, well, how do I know where I'm supposed to take KVL and where I'm supposed to do KCL, right? And understandably so, right? Because we haven't done that many of these yet. Part of it is practice, but the other part is just what I asked you when we were stepping through this, right? When you're looking at this, we know that we need everything in terms of my inputs and my outputs. I don't have a way to get I2 in terms of my input and my output from KCL, right? I don't. What I do have is a way of getting my inputs or I2 in terms of my output through KVL. That's how you know which KVL to use, right? So let what you need to come out of this guide you on what decisions to make, right? We can reduce this, right? So where are we going to start, right? Well, you can really start with either of these expressions here. I'm going to start with KVL, right? So we'll start with negative ER2 plus EC plus ER1 is equal to 0. Okay. Well, we know from our truths that, and from Ohm's law, that we have this. EC is already EC, so we'll just leave it. And R1, well, R1 is equal to what? R1 is R1 times IC. That's equal to 0. Okay. Now, you could do this a very roundabout way if you wanted, and it would come out, which is the way that I've done it. But we're going to do it a different way today, not the way in my notes. Okay. So what do we need now? We need I2, right? We need I2 in terms of EC, right? Well, how are we going to get that? Well, we know that I2, right? If I rearrange my KCL, I2 is just equal to what? Well, it's going to be IC minus IN, right? So let's substitute that in for I2. Negative R2 IC minus I in plus E sub C plus R1 I sub C is equal to 0, right? So we're almost there, right? We just need to change our ICs, and we have an equation for IC already, right? IC is just C E dot C. We get negative R2 C E dot C minus I in plus EC plus R1 C E dot C. 0. Do a little algebra, separate our equations, right? And we'll get CR1, C times R1 minus R2 E dot C plus E sub C is equal negative CR2 IN, right? If we're doing our algebra, where does that come from, right? Remember, if you're going to distribute this out, this is negative C R2 E dot C plus C R2 IN, right? That's what it is. Okay. So just to make it look nice, right, we will divide it by CR2, negative CR2, right? And IN is equal to CR1 minus R2 . There it is. Oh. Could you algebra this more if you wanted? Sure. Sure. Do you have to? No. It's fine.
Could you explain the R1 minus R2 thing? What happened there again?
This guy right here?
Yeah, like what happened from that step above that to getting to there?
All right. So negative C R2 E dot C plus. So that leaves me there. I'm just grouping like terms, right? So plus R1 C E dot C. So if I group my like terms, I've got C. I guess it should be R2 minus R1, right? My bad. This is why Dr. D doesn't like to do problems on the fly. This is R2 minus R1. Negative, so miss the negative sign, minus half a point. I'm down half a point today's lecture, guys. I don't know how it's going to work for me.
Oh. Thank you. You just did a lot of algebra without writing it, so I guess I was lost there at the steps, basically.
Yep. I mean, I guess technically we could take that out, right? If we really wanted to. If I pull the negative, right, that's going to be R2 plus R1 dot C. Because I divide out my C's, the negative sign's still there, so well, I guess that doesn't do that. That just makes it. Sorry, I got ahead of myself. So be R1 minus R2 times E dot C minus 1 over C R2 something like that ish. The other way that I did it, which is in my notes, which is the way that you'll get it when I post at the end of the week for the example problems, is it's a little bit longer. Does a few more substitutions, but gets us in the same arena. You guys, any questions? A lot of this is going to boil down to creative algebra on some level, honestly. Right? You're going to have to manipulate equations algebraically to make them be in terms of the variables of the.
Dr. D,
Yeah.
can you, on this page even, just write out the traditional mathematical truths that we would apply to these types of situations?
Like these, Sean?
Yeah, I was just wondering if there were any more, because I have those down, but I wasn't sure if it would be different if we were messing with inductors or yada yada.
So if you had an inductor in here, right, which we don't, but if you did, the inductor truth is just E, so the L is equal to L I dot L. That's the only one we're missing in this problem. That's the only one we're missing. Oh. All right. Any other questions?
Yeah. Is there ever a case, since for the last two questions, it's been just automatically adding the two components that are in series? Would there ever be a case when we would subtract two components that are in series with each other?
Not unless you have like a really weird configuration. You would need to switch the direction of current in between the two, which it's not an easy trick to pull off. Cool. All right, any other questions? All right. Well, here's everybody's other favorite topic from circuits, right? Op amps. Right? Everybody loves op amps. Who doesn't love a good op amp? You know what? I should ask Professor Bullock if he wants to come in and do a guest lecture on op amps. And so what is an op amp? If you said it's an operational amplifier, you're triggering me because you're just repurposing the abbreviation. What does it do? What does it do? It's a modern electronic device that is used to amplify or gain an input voltage signal, right? So if you heard the word amplifier and you thought this is going to make my signal bigger, that's what it does, right? It's designed to make your signal bigger. However, depending on how we use it in certain configurations, we can do so much more with op amps, right? We can use them to filter. We can use them to gain or attenuate signals, right? So why do we use them? Well, the main reason is for amplification, right? You have a very low signal that you need to amplify to read, right? We've all used strain gauges. Strain gauges typically have like millivolt signals. We use an amplifier so that we can actually see the differences in our signals, right? In circuits, to construct filters and remove a desired range of frequencies, right? So like I said, there's more than just amplification, right? In this figure, this shows, figure one shows a schematic for an op amp, right? So is this an inverting or a non-inverting op amp? What do you guys think?
Non-inversion.
This is actually an inverting op-amp. It has the negative terminal toward the top. Right, so this is going to be an inverting op-amp. Here is an equation for our output voltage. So before, when I said you're going to have things in terms of E in or I in and E sub C / E sub L, right, as our outputs, op-amps are a little bit different because really what we care about with an op-amp is how much am I putting in and how much am I getting out. So we're going to talk about op-amps as having some input voltage and having some output voltage, right? And the way that we determine that is through this equation. Our output voltage is K times the differential between EB and EA. Typically, our gain is really high. It's about 10 to the 5th, on the order of 10 to the 5th. Right. So why give this to you right now like this? Because we're going to compare our modeling, what we do and what we get out to this to see if we can figure out what K is. Right? All right, well, let's get down to brass tacks here, right? How do we analyze them, right? On the ball with the questions today, Stu. How do we analyze these things? We're going to treat it as an ideal op-amp. So what does that mean? What does that mean? Well, it comes with its own rules, right? An ideal op-amp says that the input terminals of the op-amp draw negligible amounts of current. Right? So essentially, this is saying that the input current is approximately 0. It draws approximately 0 input. All right. The voltage difference at the input terminals, EB minus EA, is also 0. So EB minus EA. Right, so this is interesting, right? Because this says that EB minus EA is approximately 0. Well, let's just use the hard equals there. It's equal to 0 for ideal op-amps. So therefore, EA is equal to EB. Okay, and our gain is infinite. K is infinity. So, well, those things don't seem super helpful, right? They don't. It's all about how we set it up, right? If we use a negative feedback configuration from the output terminal to the inverting terminal, this causes the second condition to be true. That all of the op-amps in this text, all the op-amps in our textbook are configured as such, right? So they are all configured as inverting op-amps in a feedback configuration, right? And it causes EB to minus EA equal to 0. So that's great. Why don't we just do one? Why don't we just do one? We're going to do one the long way. Right? So here's our scary op-amp, right? Here's our scary op-amp. It's got some input voltage, right, and some output voltage. We want the relationship between input to output. Okay. So we're going to have our schematic, right? That's step 1. There it is. There's our schematic. So I will doctor this a little bit. That's I1. Here's my node. I'm calling that node A, right? Node A is going to have some IA coming out of it and some I2 going across the resistor, R2. We want to figure out how can we figure out our output voltage? Okay. So let's write down our mathematical truths. But before we do that, I want you guys to notice something here. This terminal, the positive terminal, right? The non-inverting terminal. What is EB? What voltage is that on EB?
Would that be 0 since it's connected to ground?
Yes, it's ground, 0. So EB is equal to 0. Let's keep that in mind, right? In fact, why don't we write that down after we get through our inputs and our outputs, right? Because guess what? Our input is E in and our output is E out. Why? Because the problem specifically asks us to figure out the output and the input and output relationship, right? And for an op amp, that's what we're interested in. How much do we have coming in? What's my signal coming in? What's my signal coming out? That's what we need. All right, so mathematical truths, right? As Matt said, EB is equal to 0 because that's ground, right? And ground is going to be 0. So for an ideal op amp, what are our things? Well, we know that EB minus EA is equal to 0. And if EB is 0, wait for it, then EA is 0. That's huge. It's huge. And we'll see why in a second. What are my other ideal op amp truths, right? What are my other ideal op amp truths? Well, if we look back in our notes, IA, right? IA, the current coming into the op amp has to be approximately 0. So let's write that one down too, right? Because this is an ideal op amp, IA is approximately 0. So I can do my KCL at node A. Remember, what did I have coming in? I had I1 coming in, right? So this is going to be I1 minus IA minus I2 is equal to 0. All right. Because IA is negligible for an ideal op amp, we're left with I1 is equal to I2. This whole thing this whole thing is just, this is melting away, right? It's just melting away.
Why is it minus I2?
Let's go back to the thing. Go back to our diagram here, right? So I'm at A. I'm here at A, right? I've got I1 entering A. I've got IA and I2 leaving. So the algebraic sum of my currents has to equal 0 at that node, which means that since I1 is coming in, I've got I1 minus IA because it's leaving, minus I2 because it's leaving is equal to 0. But we're dealing with ideal op amp. That's 0, so it's I1 minus I2.
Okay.
Or I1 is equal to I2, right? Which is also interesting and helpful. Okay. What else do we have? Well, I've got 2 resistors here, right? And so I should probably write down, E sub R is equal to R, I sub R. And I'll write this down too. E naught is equal to K, EB minus EA. Write that one down. What time is it? All right, we got just enough time to tie this up. Okay, what if we had a capacitor? Well, you should write the capacitor equation. Well, what if we had an inductor? Well, then you should write the inductor equation. We only have resistors here. And if we wanted to be really specific, right, we could say, we could write this, and ER2 is equal to R2I2, right? We could totally write that if we wanted to. So how do we do our reduction, right? Do we do KVL for this? No, we're not going to do KVL for this. This particular op amp does not need us to do KVL, and we're not going to do it. What we are going to do is we're going to analyze KCL at node A, right? And so for my reduction, when we look at our KCL, I've got I1 is equal to I2. Okay, okay. Well, that's great and all, right? That's great and all, but how do we deal? Well, if I rearrange my Ohm's law over here, right? Can't I write this as I1 is equal to ER1 over R1? And I2 is equal to ER2 over R2, right? Can I just rearrange that and leave it like that? Sure, right? But Dr. D, that doesn't help solve the problem, right? That doesn't help solve the problem of getting things in terms of our input voltage and our output voltage, right? It doesn't. Well, it doesn't. Well, let's go down this rabbit hole with me for a second. All right. So if I plug those things in, what do I get? Well, I get ER1 divided by R1 is equal to ER2 divided by R2. Okay. So let me ask you all a question. What is a voltage drop? What is it? We talked about it at the beginning of class. What is a voltage drop?
The change of potential between 2 points.
Exactly. So if I look here, how much voltage do I have coming into that resistor R1?
Ian.
It's EN. Not Ian, but EN, right? We're not going to do the Jeff thing. It's not going to happen. All right, so how much is coming out?
Ian minus R1.
EN minus R1, right? Or, right, another way of saying that is how much do I have on the other side? How much voltage is present on the right-hand side of resistor 1? It's called out, right? It's called out on our diagram.
E sub A.
E sub A. I have EA here, which also means that I have EA here. How much voltage do I have coming out of R2?
E0.
Yeah, my output voltage. Okay. All right. So if the voltage drop is just the difference in voltage between 2 points, right? Couldn't I say that ER1 is just EN minus EA?
Yes.
Yeah, right? Can I say that? Well, if I do that, something interesting happens here, right? I'll get EN minus EA divided by R1 is equal to, well, this is just EA minus E out over R2, right? But wait, there's more, he says. EA is equal to 0, right? We wrote that down in our truths over here. EA is just 0. So if EA is 0, this is EN over R1 is equal to negative E out over R2, right? There's our inversion. Right? It flipped signs. Now we just need what? Now what do we need to do? Now we just need to get our variables opposite each other, right? Well, we're kind of there. But not all the way. Kind of there, not all the way there. So we wanted an expression for E out, right? So let's solve for E out. There it is. Op amp accomplished. There's a longer way that you can do this, and it requires you to take the limit, right? Plug all this stuff into E. E naught is equal to K times EB minus EA, right? You can do that, but it's going to get you back to this particular solution, right? Notice this is in the format of this. So in that regard, what is the gain of my system? And then what is the gain of this system?
0.
Is it?
Well,
So
if EA
what-
is 0 and EB is 0, then K would be 0.
Right. It's negative R2 over R1. That is the gain that we're looking at. Remember, this equation is for real op amps, right? When we apply our ideal stuff to it, obviously that EB minus EA is 0, right? But remember, it has infinite gains, right? But when we do our analysis, right, we're left with this, right, which has a similar form. So the K is just going to be negative R2 over R1. So that's telling us what? If we wanted to amplify this signal, right? Wanted to amplify this signal, right? Obviously it's inverted, which we can deal with that too. But if we wanted to amplify the signal using an op amp in this conversion, we would want R2 to be much larger than R1, right? To increase the amount of amplification that we have. Okay. That's where we're going to leave it.
Dr. D,
Yes.
can you explain again how you substituted that numerator into ER sub 1?
This EN, that one?
Yeah, the EN minus EA.
Let's go back to our diagram. Okay. So if you're going around our circuit diagram, right? We have EN on this side of my resistor. And I have EA on this side. How do I know that? Well, right here. Right? EA. That's how much is coming in. Remember, this node doesn't change the amount of voltage. The only thing that changes the amount of voltage, right, is if it goes through an element. That's going to create a voltage drop. What is a voltage drop? Another way of thinking about a voltage drop is the voltage drop is the amount of voltage that I am going to lose as the voltage passes through, right? So if I know EN and I know EA, then ER1 is just EN minus, right? Just EN minus EA. ER2 is EA minus E out because I have E out on this side, right? So you can substitute those in because remember, E sub R is actually the change in voltage that you're getting, right? When you measure a voltage drop, you're not measuring the voltage on the other end of the resistor. You're measuring how much voltage the resistor is eating.
Okay. And we're saying E out is the ground, right?
No, E out is how much. So notice how this is drawn over here, right? We've got terminals. This means we're going to be measuring across here, right? We're going to be measuring the difference between what we have on our op amp and ground, right? That's what we're measuring. So it's the output voltage. if there was a wire here, right, connecting those 2 points, then it would be ground, right? But there's no wire there. Remember, when we make measurements in circuits, we often use ground as one of our reference points because we know what that voltage is, right? So you're measuring the reference, you're referencing the output voltage to ground in this case. You're essentially finding the voltage drop that it takes from the end of the op amp to ground, right? That's what you're finding. Okay. All right. So we're going to leave it for today.
This stuff is tough.
Next class, we will, actually, next class, we'll keep going with this. Guys just have more rust than others. It's fine. This is stuff that, right, you just need practice on, right, and you need, so make sure you're coming to office hours and doing all that stuff.
Do we have participation for this week?
I haven't posted anything. I'm gonna figure it out today. Likely it will happen next class. All right. Have a great rest of the day, and I will catch you this hours or next class. Yep.
Thank you, Doctor. You have a good one.
Take it easy.
Yeah, I'll probably try to come to office hours later today or tomorrow.
All right.
Yeah, but thank you. Have a good rest of your day if we don't see you.
All right. Sounds good, guys. See you later.
Bye.